Okay, our second speaker is Neil Denton. He's going to talk about incremental task and motion planning, a constraint-based approach.
Thanks. So we're using incremental constraint solvers to do task and motion planning. Robots should do useful things, like clean our room or make us a sandwich. These domains have many steps, many objects, and many degrees of freedom. We want a plan to give us the steps, the actions, and the motions for the robot. Planning algorithms should have certain properties. They should be complete, they should be general, and they should give us good performance. We achieve a balance of these properties using incremental constraint satisfaction. So there are a lot of approaches that make different trade-offs in the space of properties. We aim for this middle ground that balances all of them. And we do this by leveraging incremental constraint solvers. So in a typical TMP scenario, you have some start state, some goal condition, and you want to plan from the start to the goal. TMP combines discrete decisions about actions and objects and ordering with geometric decisions about collision-free motions. For real-world action, we need both discrete and geometric reasoning. We also have interaction between the task and motion layers. When the robot picks up some object, this changes the collision-free configuration space, which changes where the robot can go. And we have coupling between objects. When the robot moves this tray, objects on the tray also move. Completeness is a tricky issue in TMP. So task planning alone is complete, so we know if there is a plan or if there's not a plan. On the other hand, sampling-based motion planning is only probabilistically complete. So if we get a plan, great. But if we don't, this doesn't mean that no plan exists. So when we're doing task and motion planning in high dimensions, this means that probabilistic completeness is really the best we can do, and we cannot definitively rule out failed actions because we haven't proven that they're infeasible. So in a typical TMP setup, you have some task planner that finds high-level plans and some motion planner that looks for the corresponding paths. If it can't find the paths, then there's some kind of feedback to the task planner, and this iterates. On the task planning side, you could do heuristic search or constraint-based planning. For motion planning, you could do optimization-based or sampling-based planning, and then a number of approaches combine these together. So we're starting from the same high-level layout and aiming for this balance of properties. For the input, we take a specification for the task side and for the motion side. The specific notation isn't too important. We compile these to constraints and to geometry, and this constraint compilation is well covered in the literature. And then the output from our algorithm are the actions and the paths for the robot. Now we open up those boxes, we use a sampling-based motion planner from OMPL, and we implement an incremental constraint-based task planner using the Z3 solver. This incremental task planning is the key new feature in our approach. So really, we're using the constraint solver as a nice way to do search in the task space. We find a high-level plan. If the motion planner can't find the corresponding path, this becomes a new incremental constraint for the solver, which picks up where it left off to find a different high-level plan. We can also remove these incremental constraints when we need to revisit operators to ensure completeness. Solving these constraints incrementally gives a 10 to 10,000 times speed up compared to solving from scratch. So we have put together a general task planner. We can incorporate rich constraints like energy use or path length using these SMT solvers. We are probabilistically complete because we incrementally revisit failed operators with increasing search depth, and we get good performance using this efficient encoding and these fast incremental solvers. So we have this nice balance of properties. So to test scalability, we increase the number of objects and the necessary plan length for the scene. Both of these tests make the discrete state space larger, which makes task planning harder, which gives a harder constraint satisfaction problem. We compare our results to a benchmark planner that is also probabilistically complete and manipulation focused. Compared to the benchmark, our approach scales much better, so after just a few objects and a few steps, we have order of magnitude improvements in performance. So we're building on powerful tools, incremental SMT solvers and sampling-based motion planners. There's a whole community that is improving these solvers. They're really great tools to use. We put together this incremental framework for task and motion planning. we can do general actions like stacking and pushing, we are probabilistically complete, and we get good performance. So, thank you very much.